Assalamualaikum dan salam sejahtera kepada semua. Hari ini kita akan lihat satu lagi equation yang special dalam bab ini, iaitu Bessel's equation ataupun persamaan Bessel, di mana dalam kelas yang lepas kita dah lihat yang Bessel equations ni have a very vast applications in physics, electromagnetic, wave and so on. So now let's receive some example on how to solve Bessel equation by using Frobenius method. Okay, let's see this example. Find a Frobenius solutions of Bessel equation of order 0 for x square y double prime plus xy prime plus x square y equal to 0. Okay, before this, we saw in class that the general form of Bessel equation is x square y double prime plus xy prime plus x square minus v square y equal to 0. So obviously, in this example, v square is equal to 0. So let's solve this Bessel equations. Alright, so because x equal to 0 is a singular point, so we can use Frobenius series, which is in the form of y equal to summation an xn plus r. Okay, and then we substitute our Frobenius series in this equation. So we will have this whole equation. Okay, then we'll collect all the same power of x and rewrite our equation, and we will get this form. Okay, as usual, because the summation index is different, so for n equal to 0 and n equal to 1, we will find the equation and then we will sum up with n equal to 2. Okay, so that we will have this equation. Okay, so for n equal to 0, we will have r square a naught x r, and for n equal to 1, we will have r plus 1 square a1 xr plus 1, and then we will collect all the index with the summation index begin from 2. Okay, so in here clearly we can see that this one is the initial equation. So we will have r1 equal to r2 equal to 0, which is in this case is a repeated roots, case number 2 in Frobenius series. And the other terms, we will have a1 equal to 0, and we will get recurrent relation for n equal to 0 and larger, which is an equal to minus an minus 2 over n plus r. Then, to find the first solution of this second order Bessel equation, so we will substitute r equal to 0 into the recurrent relation. So substitute the r equal to 0, we will have this recurrent relation. Okay, and because our a1 is equal to 0, we can see that a naught is equal to 0 whenever n is odd. Okay, so whenever n is n equal to 1 or 3 or 5, 6, 7, 9 and so on, when n is odd, we will get an equal to 0. So in here we just consider for even n. So for even n, for n equal to 2, we will get a2 equal to minus a0 over 2 square. N equal to 4, we will get this one, and n equal to 6, we will get this one, and so on. After n equal to 2k, we will get this function, these terms. Okay, how to get to this general form? Okay, we can see that when we iterate for some n. Okay, we can see in here it's all even, 2, 4, 6. Okay, so we can write it as this 2, we can write it like 2 times 1, 4 is 2 times 2, and 6 is 2 times 3. So in here we can rewrite it as a0 over 2 times 1 square. From here we can see that the sign is alternate. For example, for n equal to 2, we have minus. For n equal to 4, we have plus. And for n equal to 6, we have minus. So for alternate signs, will we use minus 1 to the k. Okay, for example, in here, when k equal to 1, so you will get the original terms. And for here, because we have this one, and if we write it like this, minus 1, because in here we have 2 in here, so put it in 2. Okay, and then we will have 2 times 2 times 2, 2 a0. Okay, so you will get this one, and so on. So you will have to rearrange. Okay, for this one, if you rearrange, you will get minus 1 square not over, because we have 2 in here, and then we will have 1 times 2 square. We have to rearrange our terms. Alright, for example, for n equal to 6, okay, so you will have the minus a0, and then in here you will have 2, 1 times 2 times 2 times 2 square times 2 times 3 square. Okay, so because this one is 3 in here, okay, so you will have 3 in here. Okay, and then you can see that the terms in here, there is 1, 2, 3, and 2, 2, 2. Okay, so this one is 3 a0 over, so this is 2, 2, 2 square, because all this one is square, but it is 3 times, and for this one we have 1 times 2 times 3 square, or we can write it as minus 1, 3 a0 over 2 times 3 factorial square. Or in general, you can write it like this. Thus, the first solution of our differential equation is this. Okay, so just substitute r equal to 0 in here, and because from the previous slide we use n is equal to 2k, so you have to substitute n with 2k in here, and your 2k is the one you get before. Alright, so we got our first solution, and then for the second solution, okay, the formula to find the second solution is we have to differentiate the first solutions. Okay, but with the R dependence. Okay, by using this one, or when we expand this one, we will get this one. Okay, so in here, we need to find the derivative of an. So how to find the derivative of an? Okay, to find the derivative of an, first, we have to keep the R dependence in the recurrent relation. Okay, so our recurrent relation is an r equal to minus an minus 2 over n plus r over 2. Don't substitute the value of r in this recurrent relation yet, because if you substitute the value of r, you will get back the first solution because we have repeated roots. Okay, so we keep the R dependence in the recurrent relation, and then we iterate our recurrent relation. So because we know that A1 is equal to 0, so A3, A5, A6, and all the odd n will equal to 0. So we just consider the even n, which is 2, 4, 6, and so on. Okay, so we iterate it. So this one for n equal to 2, you will have A2 equal to minus A0 over 2 plus R square. This one n equal to 4, you will have A4. N equal to 6, you will have A6, and so on until n equal to 2k. You will have A2k equal to this one. Okay, why 2k? In here k is 1, 2, 3, and so on. Because as I explained before, in here we have 2, which is 2 times 1. 4 is 2 times 2, and 6 is 2 times 3. Okay, so we going to use 2k because it's an even terms. After we iterate the an terms, so we need to find the derivative of dn over dr. Okay, so to do this, we use the ln in both sides of our a. Okay, so put ln in both sides and use the properties of logarithmic function, and you will find this equation. Okay, and then will we differentiate this one with respect to r. Okay, log function is a special function. Okay, because when we differentiate this one, Okay, so when you differentiate ln, you will have a to k r over a to k. Right. Okay, so you will have this one. Because differentiate this one with respect to r, you will get 0 because this one is a constant. And when you differentiate this one, okay, you will have these terms. Okay, so this term is a summation of this term lah, 1 from k equal to 1. Okay, because from k equal to 1, you will get the first term. When k equal to 2, you will get the second term, and so on. So we can write it as in here. Okay. Okay, then our a prime is given by this equation. Okay, and then after we get the d over dr for our a and r, okay, after we get this, then we substitute the value of r. Okay, so substitute r equal to 0 to this one. So we will have this rearrange. Okay, because this one is just a recurrent relation that we get when we substitute r equal to 0, which is this one. And this one is here. Okay, so we will rewrite this one as this. Okay, so let hk equal to summation of 1 over k. And then we will get this one. So our second solution for the Bessel function, x square y double prime plus xy prime plus x square y equal to 0 is this one. Okay, so that's all. I hope you will understand. Thank you.